giving this set of lectures. I think he's going to basically teach 10 hours of lectures, okay? So I think, okay, he's well known at RRI, but let me anyway formally introduce him. So Professor Majumdar is a senior scientist, senior researcher in CNRS, so which is called Director of the Research, Class Exceptional, okay? So he is also a Vajra faculty at RRI, so he has been visiting RRI frequently, and this time he is visiting us for about 2+ months, basically, okay? So he has received numerous awards, and he has been into editorial board of many journals, and recently he has also become a chief editor of, I think, Journal of Physics A. Yeah, so he has recently actually published a book on the same topic, so, and he is going to basically tell us about experiment records, and yeah, Satya, welcome.
Thanks a lot, Sanjeev, for your kind introduction and for the invitation. I need a mic? Yeah, so thanks, Sanjeev, for the introduction, and it's very nice to be back here at RRI. And so the Sanjeev asked me to give this set of lectures, and since, as he said, that we recently wrote a book on this subject, so it was, you know, it will be easier for me to just follow the book and give this course, and that's why I agreed. So this is a subject, I mean, the name sort of kind of suggests that maybe it's a subject on statistics, but it is. But as you will see that, you know, it has also important connections to physics. I mean, so it's actually really at the crossroad between statistics and physics, these two disciplines. And many of the problems in statistics you can actually solve by using techniques of physics, as we'll see as we go along. So this will be a set of 10 lectures. I'll mostly use the Blackboard, but on the first day, I mean, I thought I'll just give you an overview and some kind of perspectives before going to the Blackboard and working out things in details. And this is very important to have an overview because, I mean, it's like going to a city, you know. I mean, when you visit a new city, I mean, I always do that. I mean, I'll always find the tallest tower and go to the top and have a general view of the city before actually going to the details. And so I think that's quite important to have that. So basically you want to ask, you know, what are the main questions and what are you studying? What do you want to solve? You know, that kind of questions. So I'll just, you know, give an overview of this, and then from next lecture onwards, I'll go to the Blackboard and work out in details. Since it's a 10-hour lecture, I have to do something on the Blackboard. All right. So what is extremes? I mean, so, you know, extreme events, you know, they are rare events. They don't happen every day. But if and when they happen, their effects can be devastating, like earthquakes, tsunami, flood, then whatever, you know, COVID and many other things. And so ideally, of course, I mean, what you would like to have is to, you know, to have a model that can predict, for example, earthquakes or tsunami or whatever. But of course, I mean, we don't have such models, I mean, which can be very good in prediction. Okay. So when you don't have such predictive models, so what can you do? So what people do is, you know, you have to collect a lot of data, you know, a lot of statistics essentially, and based on the statistics you construct, I mean, this is the job of the statisticians, you construct some basic models, operational models, and based on the statistics you try to say, okay, there is some probability that earthquake might happen somewhere, okay, and that kind of thing. So therefore statistics is very important. I mean, you know, you have to analyze time series data of either, you know, any of these things. And in fact, with the, you know, in this sort of modern volatile days when the climate changes are happening almost very regularly, so it's actually become very, very important to study this, you know, the time series of these extreme events. And okay, so in fact, I mean, this subject has been around for many, many years. I mean, almost for 100 years in statistics. So there are standard books like, for example, this book by Gumbel, Statistics of Extremes. Then there's in finance, there's a lot of work. Because, basically this idea of the extreme statistics apply to any time series. It could be a financial time series, which is stock price, or it could be climate studies, hydrology, sports, all kinds of things. So far, it was mostly concentrated into this area of statistics. But as I said, that more and more, actually, one is finding applications in physics, in particular in statistical physics, and I'll give many examples of that. So, for example, random walks and disordered systems, random matrices, number theory in mathematics, and so on. So these are the sort of new applications. So because of these many applications, this field, is essentially becoming very fashionable, if you like. Okay. So just to give you some example of time series. So for example, finance. We are just talking about finance. So let's start with the finance. So this is I just found from the internet. It's not last week, I think 2 weeks back. So you can see that the Adani stock went down because of this report from the SEC from New York. And so this is the price of this Adani Group's market value, for example. So this is the typical time series that you have the data basically. And so by extreme, one means, for example, the maximum of the stock price in a given maturity period, or the minimum, which is here, the global minimum or the global maximum. And of course, they are very important because, typically if you are, playing in the stock market, then you want to buy the stock when its price is minimum, right? This is the point where you want to really buy because it's very low price. On the other hand, when it's maximum, you want to sell the stock, okay? So therefore, you need to know not just the value is important because that gives you your profit or gain or whatever compared to the starting point. And but it's also important to know when does the extreme occur, this maximum occurs, for example, or when does the minimum occurs. Of course, these are random events, so you cannot say it will happen like on September 9th or something, but you have to say with some probability. You have some distributions of the time at which the maximum occurs or the time at which the minimum occurs. So these are the typical questions that one is asking in extreme value statistics, that is, given a time series, a random time series like that, what can we say about the statistics of the value of the maximum, the value of the minimum, or the time, for example, at which they occur and things like that. Okay? There can be other time series. So for instance, this is the average monthly temperature in Bangalore. You can see that, of course, in April, this is the hottest month. So this is the maximum of this time series. And the minimum is in January, cold, and so on. Now, so we are talking about the extreme value statistics, but what is the sort of difference from the average? So just to give you a simple example, suppose that you collect your data for the hourly temperature, let's say in a given day, every hour you record the temperature in a given city, like in Bangalore, for example, during a month. Okay. So let's say in month of December right now. So if I measure the temperature at 1 o'clock, 2 o'clock, 3 o'clock, and after 24 hours, so you get a set of 30 data points, right? These are your temperatures on a particular day. And you do it for every day for a month. So that gives you a table of 30, basically, 24 by 30 table. And so what you can do is, as a typical thing to do, you can compute the average daily temperature. That means you take your 24-hour data points in a given day and you divide by 24, okay? So that gives you the average temperature of a day. And you can actually draw the histogram. So you have a sample of 30 days. So first day you have some value, second day you have some value, and you can draw a histogram. So this will give you, let's call it P1 T bar, which is the histogram of the average daily temperature. And this is typically what you find in any weather stations and so on. But you can also get the maximum temperature in a given day, right? So suppose that day one, you find out of these 24, you find out the maximum value. So that's a Tmax, it's a number. And this number varies from one day to another day to next day and so on. So again, you can draw a histogram of this Tmax, okay? Now, these two histograms, and then you can compare the average of a given, the average daily temperature, their distribution, and their, maximum, the distribution of the maximum temperature. And it turns out that they are actually quite different, okay? usually. Okay? So that means, average is not a representative of the maximum. The maximum are really outliers which occur very rarely, and so their distributions, the histograms, they are quite different from the average histogram. Okay? And so therefore, the average is very different from the statistics of maximum or minimum. You can do the same thing for minimum. And so this is, some experiment you can do. I mean, just go to the internet and find out the data and just plot it on your own, and you will see that they are not the same. Okay? So it's a good exercise to do that. Okay? So therefore, one would like to know, and now for the average, there are many results from mathematics, central limit theorem and other things, for which one knows quite a lot about the average. But the the extremes, their distributions, this P2, that's not so easy to, that's not so well known in some sense. And so our main goal is to understand the statistics of this maximum or minimum. Okay? So that's the main question. And so let me give you another example. So this is what you see here is a time series of the water level on the Nile River near Cairo from 622 to 1284 AD. Okay? So this this is a sort of raw data, and this black line is like the average over some window of 10 days, basically. Okay, and so if you look at the average, this is the black line here. Okay? That's varying like this. Whereas the raw data, it shows extreme, outlier, these big fluctuations here and there. Okay. Now imagine that you are a civil engineer, and you want to construct a sort of dam on this river. Okay. Now, what would you look for? I mean, you have at your disposal the data for the last, let's say, 600 years. Okay. Now, would you look at the average height of the river? That's not the point, because if you construct your dam on the average height, then if somewhere the water level goes above the average, it will be completely flooded. So therefore, what really interests you is not the average. What you are interested in, how the extreme over some window of these things, how these outliers, how they are fluctuating, right? So I mean, what is the statistics of that? What's the distribution of the large values, basically? Because then your dam height should be bigger than those things. Okay. So it's a very practical, applications. And same thing, I mean, if you look at the rainfall or temperature time series, I mean, this is some, rainfall day, precipitation steps in some place. And you see again, there are these extreme events. That means some days there are a lot of rains, and some days maybe very little rain, and so on. So again, you want to know again, the statistics of those outliers or extremes. And this is actually a sort of very important and crucial for the global warming studies. As you know, these days, there is a lot of temperature fluctuations, climate statistics, and people are all the time analyzing the extreme statistics or extreme fluctuations. And this sort of has become a sort of very important and crucial tool in the study of climate studies. Okay. And again, you see that the average is the green line here is very different from those outlier statistics. All right, so these are the sort of typical example that you find in any common time series. Now let me sort of mention the connection to physics. Okay, so why are we interested in, as a physicist? Why would be interested in this? Okay, so as you will see, the extreme statistics also play a very important role in physics. So let me start with the first example. Okay, but before that, so let me sort of say the general setting. Therefore. So you have a time series, x1, x2, x3, xn, let's say, okay? And like we saw many examples of the time series. Now, these are random variables, okay? It fluctuates, as we saw, for example, the daily temperature, I mean, it will vary from day to day. So you have many sets like that. So there is these values, therefore, they have an underlying joint distribution, x1, x2, x3, xn, joint distribution, which means that they may be correlated. If they are independent, this joint distribution will factorize. But if they are correlated, it will not factorize. And so you don't know what the underlying joint distribution is. And this is the job of the statisticians, because they study the histogram, they make the model, and then they try to make some mathematical modeling of this joint distribution. Okay. And as I said, it can be either independent or correlated and so on. We'll come back to that more details later. Okay. So we have these entries of the time series, x1, x2, x3, xn. So size of the time series is n. And so you have a rainfall or temperature data, height of a river, stock price, etc., as I mentioned. Okay. And given, so what is our job? I mean, as a sort of these things. So given this joint distribution, you want to know what is the maximum of these entries and what is the minimum of these entries. And of course, this is a random variable because if you change the sample, you draw another realization from this joint distribution, this guy is going to change. So it fluctuates from sample to sample, and you want to know what is the distribution of x max or what is the distribution of x mean, etc. Okay? So given this joint distribution, what can we say about the statistics of x man and x mix? Okay. So this part, so the modeling of this joint distribution is basically, essentially the statisticians do that. What the physicists do is that given this joint distribution, can I calculate, for example, the distribution of x max or x mean? Okay. So this is the statistical physics part or the computation, actual computation part. And so because, if I give you the joint distribution, that does not mean that you can calculate all observables. So calculating the observables requires one additional step. So this is step 1, if you like, this is step 2. And this is where the physics comes in. So just to give you some examples where, where the extreme statistics play an important role in physics. So, so some examples from physics. So first example is something that you are very well aware of, and this is the example of a random walk. So imagine that you have a random walk. So here a continuous space, and this is time. Okay, so discrete time, let's say. So at each step, so a random walker, for simplicity, I'm just doing in one dimension. So you start at the origin, and then at each step, you just draw some random number, which is like an amount of jump. So that's independent from step to step. So this is called the noise or eta n. And then you just add to the current position this noise. Okay? So basically the walker keeps jumping, and it's like that. So again, you have a time series. So xn, position of the walker at step n. So those are the entries of this time series. And you say that, this noise you can draw from any arbitrary probability distribution. Let's call it a theta, which is normalized. And we'll see later that, a theta can be anything. You can have Levy flights where the a theta has a broad tail and so on. But for the moment, just a simple example of a random walk. So random walk appears in many, many different contexts in physics. And in particular also in ecology. For example, animals often perform random walks when they are searching for food, which is called the foraging. So it's their nest, and then they just make random walk, and then so in this context, for example, I mean, you look at so how much territory the animal has covered during a day, let's say. Okay, so that is essentially, in one-dimensional context, you can see that's a span of this process. By span, I mean the maximum minus the minimum, right? So that's this whole area, basically. How much territory the guy has covered, the animal has covered in a given time, a number of steps. So if you want to know, and this is what is, the ecologists often use, and it's called the home range. There's a territory covered by the animal in n steps. And they have to have a good idea of this home range in order to construct reserve forest and many other things. And so this is an important object. So if you want to calculate the statistics of this span, so you need to know the distribution of x max as well as x mean. In fact, they are joint distribution. So once again, you see that here, you have to know the statistics of the maximum or minimum of the positions of the random walker up to n steps. And this is not an easy problem, as we'll see later. Okay, so this is example 1. Now let me give you example 2. And this is a very classic example from statistical physics. It's our disordered system, statistical physics of disordered systems. And this is called the directed polymer in a disordered medium. Okay. So this is, as I said, this model is a paradigm in statistical physics because it has played a very important role in many, many disordered systems. By disordered system, I mean, for example, spin glass, where you have an Ising model, and you have a coupling between the spins, which is random but frozen random variable. And similarly here, you have a directed polymer in a random medium. So let me define this model first. It's a very simple model. So imagine that you have a square lattice, okay? At each site I of the lattice, you just associate an energy, epsilon I, okay? So these are sort of, quenched random variables, meaning that each of the epsilon i's I choose from some distribution. I just draw random numbers from this distribution, and they define my medium, okay? And it's called disordered because they are not the same. It's not a homogeneous medium. And we assume that they don't vary with time on a time scale that you are observing your system. In that sense, they are called the quenched variables, okay? So they're given frozen variables, okay? And this is your disordered medium, okay? Now, once you've defined the medium, so after that, you consider another object on this medium, in this medium, if you like, and this is a polymer. So by polymer, I mean just a straight line, for example, or you can think of it a random walk going on this disordered environment. So the polymer starts at origin, and for simplicity, you just take a directed polymer. Directed means that it can go only in the east or north. It cannot go, I mean, that's not very important, but I mean, just for simplicity of the presentation. So you think of a directed polymer path. So for example, of n steps. So here is an example of 10 steps. So the blue line here. So the polymer starts here. It moves a random walk you can think of, and it go 3 steps up, and then 3 steps to the east, 2 steps up, and 1 step there. Okay? So this is one configuration of the polymer of 10 steps. Okay? Now, associated with this configuration, you define an energy of this path, if you like. And what is the energy of the path? So this is the sum of all the epsilon i's that are sitting. Because remember, the epsilon I is your medium. So the polymer goes through all these lattice sites here, and therefore the energy of the path of the polymer is just a sum of the energies at those sites through which it passes. Okay? So for each path of the polymer, I can associate an energy, which are these quenched random variables. Okay? Now, this is only one particular configuration of this directed path. You can have many possible configurations. There are 2 to the power n if you have an n-step walk. So you have a 2 to the power n because each time you can either go north or east. So you have a 2 to the power n possible directed paths. Okay? So here in this example, you see this blue one that I showed you before, and red one is another polymer path, which is also of 10 sites. Okay? And so it has also its own energy, okay, which is typically different. So energy actually fluctuates from path to path. And then what you want to know is the ground state of the polymer. That means which is the path or the optimal path the polymer chooses to go, I mean, when it's a size of n steps, right? So you have out of 2 to the power n possible paths, you find out which is the path which has the lowest energy. So that's the ground state of the polymer. And this is a very important problem in combinatorial optimization because you are optimizing over the energies of different paths. There are 2 to the power n paths. So for each path, there is energy, which is the sum of the epsilon i's sitting on that path. So you calculate the energy of each path, and then you just find out the path which has the minimum energy. And this is the ground state energy of the polymer. Okay? And the problem is that, here, so you can think of this as your time series x1, x2, x3, xn. And therefore, E naught, is a random variable in the sense that for a given relation of the medium, it has a one value, basically, energy of the path, optimal path. But then when you change the medium, if you change your epsilon i's, this E naught is also going to change. It fluctuates from one sample to another sample. And you want to know what is the distribution of the ground state energy E0. Okay? So it's exactly in this, like in the spin glass problems where, you have Ising spins and there's a coupling. And for a given, set of couplings, which is like a given set of epsilon i's, you find out the ground state spin configuration which has the least energy. So that's the ground state energy, ground state configuration. You find out its energy. And then when you change the couplings, this energy will change from one relation to another relation. And you want to know what's the distribution of the ground state energy of the spin glass. Okay? So directed polymer is just one example. But any of the disordered system, you can actually cast it in the language of extreme value statistics, where the ground state energy is precisely the minimum of all possible configurations of the system. Okay? So once again, you see that the EVS, that is extreme value statistics, it plays an important role. And here in this example, you see that the x1, x2, x3, xn, so these guys, these observe your entries of a time series, if you like. Here they are corresponding to each path. So these guys are actually very strongly correlated because for example, these two paths, the blue path and the red path, now they have the sum of epsilon i's, but the point is that, some of the epsilon i's may be common, right? So for example, the blue path and the red path, they go through these common sites, this guy, that guy, this guy, shown by the black dots, okay? So they have some of the energies in common, okay? So as a result, they are quite strongly correlated. And so this is a problem of correlated random variables. What can we say about the extreme value statistics of a correlated random variables, okay? We'll come to that more details later. And so this is this is a classical example from statistical physics, of classical statistical physics. Let me give you another example from physics, which is a quantum system, okay? So imagine that you have a system, quantum system, okay, with some Hamiltonian. Think of it just in one dimension for simplicity. I have n sites, and this is any general Hamiltonian I can write in the site basis. So Ij is a bracket of the site basis on a lattice, and Hij is just the matrix element. So any Hamiltonian I can represent it in this form. And so this H here is the n by n Hermitian random matrix. Hermitian because quantum mechanics tells us H has to be Hermitian. And so you have this n by n matrix of your Hamiltonian. So now if this guy Hij, it involves only nearest neighbors, okay? So then this is the Hij will be, for example, one dimension will be tridiagonal matrix, right? So because it involves only the right neighbor and left neighbor. So from a diagonal side, you go to the right or left. So the tridiagonal matrix. And these are quenched random variables, okay, in a general disordered system, okay? And so if it is tridiagonal, that means if it only involves nearest neighbors, this is the famous Anderson model, okay? On the other hand, you can have a mean field model where all the sites I and j on your lattice, they all, these matrix elements are non-zero. Everybody is connected to everybody. So this is called the mean field model. And in this mean field disordered model, typically what you say is that the Hij is a n by n Hermitian random matrix, but the entries of this matrix, you can take them to be random variables because you don't know really what your Hamiltonian is. Only thing is that it's a Hermitian matrix. And suppose that you take this disorder, these actual energy elements from a Gaussian distribution, independent Gaussian distribution of the entries, okay, or upper diagonal entries. So therefore, it's a product of the Gaussian. And this one you can write down as a trace of the matrix H dagger H. And you write out why you are choosing this because this is, you see, if I change my basis, then under any change of basis, this guy trace of H dagger H is invariant, and therefore any physical system should be independent of the basis, your energy Hamiltonian, and the distribution of the H, and therefore this is invariant. So this is a simple choice of Gaussian random. So this is called the Gaussian Hermitian random matrix, and there's a popular name for it. It's called the Gaussian unitary ensemble because this is invariant under a unitary rotation of your basis. Okay? And this is the essentially random matrix theory. The whole field of random matrix theory is that if you give me the entries of this Hamiltonian, okay, what can I say about the eigenvalues? Okay. So if I diagonalize this matrix, I have an n by n matrix. So I'll get, because it's a Hermitian matrix, I'll get n real eigenvalues. So those are the energies of my system. Okay, these are the spectrum, if you like. And it turns out that even in this case, even though the entries are independent, these eigenvalues are very strongly correlated. I'll come back to that later again during the course. And what you want to know is, for example, again, that what is your ground state energy, which means the lowest of these eigenvalues, the minimum of these n eigenvalues. Okay, and this is the E0. And once again, so you need to know these are like your x1, x2, x3, xn. So those are like your time series entries, if you like, and you are looking for the minimum of those, and you want to know the what is the distribution of E0. And again, one sees that this is an extreme value statistics. So basically, any disordered systems, be it classical or quantum, essentially it's a problem. Finding the statistics of the ground state energy is essentially an extreme value statistics problem. Okay, let me give you one more example from physics. This is a real experiment of a granular gas. So essentially, we have some n boxes, let's say, and and you have some pith balls, basically, some very light granular balls. And what you do is you make holes in these boxes so that the balls can pass from one box to another box through this, and you just make a periodic boundary condition around it so that your total number of particles is conserved. Okay. And then what these experimental people did is, they just shake this box, okay, and they ask, what happens to these balls? What is their configuration? Where do they go? Long-term limit. So of course there are many parameters in this model. For example, the vibration, the frequency of the vibration, the amplitude of the vibration, then the height of these holes, the width of these holes, and the size of the diameter of the balls, and so on. So there are many parameters here. Okay. So you just shake it like this, and then you ask what happens. So it turns out in this big parameter space, there are some special values of the parameters at which actually what you see is what is called the condensation effect. That is, what you see suddenly is that most of the boxes, n-1 boxes, they have small number of particles, but there is one box which gets the predominantly large number of particles. Okay, so this is almost proportional to the total number of particles, finite fraction of the total number of particles, and this is a condensation. Condensate means that that all the particles condense onto this one site, and this is a condensation is real space as opposed to the Bose-Einstein condensation, for instance. Bose-Einstein condensation, if you take ideal Bose gas, and then what happens at low temperature, they might condense into the ground state. Okay, so that happens in the energy space, but here it happens in the real space. That it condense, all particles condense into the, many particles condense into this one box basically, and this box is chosen spontaneously. It breaks the translational, invariance spontaneously gets broken in the system. And so if you want to, study this problem, and you want to know typically, for example, that what is the size of the condensate, and how does the number of particles in the condensate fluctuate, and so on and so forth. Okay. So essentially, then again, you can cast this problem in the language of extreme value statistics, because what are the basic degrees of freedom here? Is just if you want to specify this configuration of the system, you have to say what is n1. N1 is the number of balls inside this first box. Here in this example there are 4 of them, and here is n2, n3, n4, etc. Okay. So if you tell me the number of particles in each box, that specifies the configuration of the system. And then condensate is basically the maximum, largest one of this, right? So it's a max of n1, n2, n3, nn. So again, you see that I can cast this in the language of this time series x1, x2, x3, xn. And this is, we are looking at the maximum of this guy. And of course, this will fluctuate from one configuration to another configuration. So if I want to know what is the distribution of the number of particles inside the condensate, so that's again another example of extreme value statistics. And okay, this problem has been studied quite a lot. People study, the experimentalists of course do these experiments, but theorists try to find models for this n1, n2, n3, nn, their dynamics, and then they try to find out the stationary state, when does the condensate occur, and so on. So there's a lot of work. I'm not going to the details of that. But just to show you that, many examples like that you can cast in the language of extreme value statistics. And similarly, this condensation phenomena you see in many other problems. For example, in Bangalore, if you look at the traffic, often there's a traffic jam. So traffic jam is an example of a condensate. It's a very big jam where a lot of cars are there, they are not moving at all. And then you have growing networks. For example, if you go to internet, and if you look at different nodes, and so sometimes a node forms, which is like a hub, which has a lot of connections. For example, Google, if you look, everybody uses Google, so almost every other site is connected to Google. So there's a giant component, basically. So that's also another example of condensation, which is the extreme value statistics. Then you have this, run and tumble active particles. When the particles move, they absorb energy directly from the environment, and they just move ballistically. And often, in some parameter space, what you find is the typical configuration of the bacteria. It's just moving like this run and tumble motion. And then there's one run, which is very big, or the giant run. So that's also another example of condensation. That's extreme value statistics. And then, okay, there are other models like discrete nonlinear Schrodinger equation, so where there's a localized wave function. And the formation of localized wave function, you can again cast it in the language of extreme value statistics. All right, so therefore, let's just say once again, remind us what is the general problem that we are looking at. So the general problem, as I said, you can think of that as if you have a time series of n entries, x1, x2, x3, xn. They are distributed by some joint distribution, okay, and which of course depends on the model, okay, and different models have different. Sometimes computing the joint distribution itself is not easy, and it depends on the model and so on. But the entries can be anything, as I said. Either it could be statistical time series like this, or it could be in the context of disordered systems. These are the eigenvalues, for example, of a random matrix, or eigenvalues of or the energy of the disordered paths of a directed polymer, and so on. And what we want to know is that given this joint distribution, we want to know the statistics of, first of all, the value of the maximum and value of the minimum. From a given realization, I pick out the maximum, I record its value, and then I see how it fluctuates from one sample to another sample. So that's the distribution of X max. Minimum, again, same thing. From this given sample, I pick out the minimum, and I look at how it fluctuates from one sample to another sample. But it's not just the values. You can also ask, and computing this, as I said, this is a statistical physics part, essentially. But it's not just the values, but you also want to know at what time, if you think of this as time, at what time does the maximum occur? Like in the Adani stock, when is the maximum? Because that's the time you want to sell your stock, okay? Or the minimum, when you want to buy your stock. So you need to know, these are also random variables which fluctuate from one sample to another sample. And you want to know what is the statistics of T mean and T max given the underlying joint distribution. Okay? And then there's the other question which is called the order statistics. Order statistics means the following, very simple. So this is the global maximum, but you can ask, where is the second maximum? Second maximum in this example is just here, right? So second maximum, or you can ask for the third maximum, fourth maximum, etc. Okay? So these are called order. That means you order in decreasing order of their values. And then, so for example, in the context of disordered systems, you can say minimum is my ground state, then the first excited energy state, second excited state, and so on. So those are just examples of order statistics from physics. And then there's another concept which is called the record statistics, which is the second part of my title, Extremes and Records. So what are records? So let me just give you a general introduction to record statistics. Okay, so this is the problem. Is the problem clear to everybody? That you give me a joint distribution, and which could be either independent or correlated. I'll give examples of both as I go along. And then our main job is to, given this joint distribution, I want to compute the statistics of X max or X mean. I want to calculate the distribution of the time at which the maximum occurs, time at which the minimum occurs. And then these order statistics. And as you saw, many applications of it. If you give me a disordered system, I have a spectrum of the energy, and these are random variables. They fluctuate from one disorder to another disorder. And I want to know how does the ground state fluctuate, how does the first excited state fluctuate, second excited state fluctuate, etc. And finally, these record statistics. So what is record statistics? So what is records? If you open your newspaper or television, you always hear about records being broken, like in cricket to anything. All the time, sports and finance and everything. And so records are ubiquitous in nature. So in fact, it turns out that Guinness Book of World Records is actually world's best-selling book, which I didn't know actually. Okay, so it turns out because people are fascinated by records. Okay, and so here is an example of the world's largest pizza. Okay, there's a crane which puts mozzarella on the pizza and things like that. Okay, so you always see these pictures everywhere. If you find internet, you will find lots of examples like that. Okay, and this is, for example, the people are fascinated by the towers, right? So every country, whenever its economy gets better, they try to construct the tallest tower. Okay, right now it's I think this is okay. So you can see this is in the increasing order. So this is here's New York City, of course, New Empire State Building, and then it's sort of increases the height, and now it's I think Burj Tower in Dubai or something. which is the tallest, and so on. Okay. So this is the records are being broken basically. Okay. And so I mean, since we are from India and we are fascinated by cricket, I mean, so Don Bradman, for example, if you look at the number of test centuries made by a batsman, so Bradman held the record with 29 centuries for a very long time, and it took 51 years to break this record, since Sunil Gavaskar, who made 34 test centuries. And then his record stayed 24 years till it was broken by Tendulkar, who has now 51 centuries, which is still a record. And there are other guys who are, still batting. I mean, Root is 35 centuries and Kohli is 30. But this guy is playing badly nowadays, so so he probably won't be able to break this Tendulkar's record. So again, these are the record values, if you like. 29 is the value of the record. Then 34 is the value of the next record. 51 is the value of the next record, and so on. And this is the time a record, survives. This record, for example, once this record was formed, it survived for 51 years, then 24 years, and so on. Okay? So again, this is records in rainfall. I mean, you see, so record means there's basically, this. So these are the records basically. Okay, I'll define more precisely. So let me define. So how do I again? I mean, my favorite picture is this time series entries 1, 2, 3, 4, n, xn. You have the maximum and the minimum. But now record, we say that a record happens at step k. So at any point, suppose here, if a record happens, that means its value there should be bigger than all previous values, right? That's the definition of a record. So that means xk, if the entry xk is bigger than all previous entries, then we say that the record has happened at step k. Okay? And so that's the definition of record. Okay? And in other words, xk is bigger, since it has to be bigger than all of them. That means it has to be bigger than the maximum of them. So you see, the records and extremes are quite closely related actually. So the occurrence of a record is conditioned on what is the extreme value currently, basically. Okay. And so once again, so if you look at the your time series entries, let's say drawn from some joint distribution, independent or correlated, and I draw this time series. And then record are those which are in red dots, because you see this guy is a record because, of course, this is the first guy, so it's a record, and nothing was before it. Second guy is a record because this value is bigger than the first guy, okay? So this is a red dot, it's a record. And the distance between, the time distance between these two records is just L1, if I call it. That's the age of a record. Then, third guy is not a record because his value is less than the previous guys, so it's not, this one is also not a record. But this guy is a record because its value exceeds all previous values. Okay, so therefore this is a record. So here we see the record is broken. So far, during this period, this guy is a record. It's a record held, like Gavaskar, for example, and then Tendulkar breaks the record. So this record lasted during period L2. Okay, and then this guy, again, these are not records. So it lasted, the record lasted for period of L3 till it gets broken here by the fourth record, and so on. Okay. So I hope the definition is clear, right? So record basically means that it's bigger than all previous guys, okay, called upper record. So then the natural question is, if I give you a series of n entries, how many records are there? In this example, you see there are 4 records, okay? So mn is the number of records in step n. So again, this is a random variable. It will vary from one to another realization. And you want to know what is the statistics of the number of records. Okay? What can you say about the statistics of number of records? Okay? And then, as I said, how long does a record survive? Okay? So this is the ages of records, so L1, L2, L3, L4, etc. And you can also ask the more detailed question like, what is the longest record? Okay? That means you are looking at the maximum of these record ages, L1, L2, L3, L11, or minimum of them. So these are the, so again, you are looking at the extreme statistics of the record ages themselves. Okay, so it's a second order problem, if you like. So there are many questions associated with records. And again, you can ask, why do physicists care about such things? is, so because there are many examples of in physics where, you see this structure. So if I plot the record value, okay, so like, for example, the number of centuries, Bradman was 29, and then it stayed for a while, then it becomes 34, and then 51, etc. So if I plot this record value, so if I go back here, so, so this is a record, and then this is the record value stays like this, then it gets broken, it becomes record, and so on. So if I just plot the record value, so what you see is that it has a staircase structure. So its value was this, it stayed like this, just one step, 2 steps here, and then it sort of, it jumps because then new record forms, and this, stays a record. That means its value stays fixed up to the point when the next record occurs, and then again its value stays fixed. So, you see, it has these staircase structures, right? If I plot the record value, and the distance between 2 records is their record age, if you like. Okay. Now, this kind of staircase structures is very common in many, many problems in physics. I mean, for example, elastic line moving in a disordered medium, vortex density in type 2 superconductors, and so on. So I'll just give an example of that. So imagine that again, you have a disordered system. This is a cartoon picture. You have a disordered system. So these points here, they are like pinning centers, if you like. If you try to pull a polymer through this disordered medium, the polymer gets pinned locally, the chain basically. I'm pulling this polymer chain. It gets locally pinned by these disorders. Okay. So typically what you will see is that you're trying to apply a force and pull the polymer, but the polymer can't move because it's stuck at different points. Okay. So then you increase your force, and when you increase your force, at some point they get detached, and when it gets detached, many of these points get detached simultaneously, so this is called an avalanche. Okay. So, a whole chunk of the line moves forward, and then again it gets stuck, and again you pull, with a bigger force. So you continuous this force F here is the pulling force, and again it gets detached. So if you look at the center of mass of this line as a function of time t, so this is an experimental picture. What you see is that it typically has, the center of mass of this line, it stays like this, and then suddenly there is an avalanche. It just gets detached, and it moves forward. It jumps, and then again it stays for a while, and then again jumps and jumps. So again you see this kind of staircase structure, and this is actually exactly these record statistics that you have seen. Basically, it stays for a while, and then it till gets broken by the next one, and then its value jumps basically. Okay? So this is an example of directed polymer in a disordered medium. But you also other examples. So for example, in type 2 superconductors, I mean, those of you know, so type 2 superconductors, essentially there's a Meissner phase, which means that, when you put a magnetic field, it cannot penetrate your sample. Okay, so it goes outside the sample. Okay, so, but then type 2 superconductor is that, if you put a higher magnetic field, then there's a phase which is called the, basically type 2 phase or Abrikosov phase, where there are these flux lines which enter through the system. So the vortex can, the magnetic field can penetrate the sample, but only in some fixed positions, okay, like a hexagonal lattice, not everywhere. Okay, so this is called the flux line lattice. So when you sort of increase this field a little bit, so these vortices, they enter your sample, and so if you look as a function of time, the number of vortices, so what you see is the number of vortices in the beginning 0, and then you increase the field a little bit, they jump, okay, a few of them, 5 of them, and then again it stays fixed for a while because the vortices also get pinned by disorder, and you increase the magnetic field, then again some vortex can come in, and so again you have this kind of the staircase structure. Okay, so the staircase structures are very common. As I said, many examples, like as I mentioned here, vortex density in type 2 superconductors or elastic line moving in a disordered medium, thermodynamic magnetization in spin glasses, fitness in evolutionary models in biology. Okay, so there again you have this fitness of a species, so that again has this kind of jump structure, staircase structures. And then, if you look at the climates problems, again you have this rainfall records and so on. So that also have these things. So there are many examples where the record statistics play an important role. I mentioned sports, and as I mentioned, evolution models in biology, where people look at the fitness of a species, how the record fitness occurs. Then, as I mentioned, disordered system spin glasses, avalanches, growing networks, then global warming, and so on. And classical theory of records, which has been well studied in the statistics literature mostly. So that is the case when the joint distribution of your entries, they are independent and identically distributed random variables. And in that case, it turns out that many results for the record statistics are universal. But what we are interested, and this is because of physical systems, in physical systems, these are not independent entries. The entries are correlated. For instance, I mean, if you look at the climate data, temperature data, I mean, if today it's hot, tomorrow is most likely going to be hot. It's not really completely cold or something, right? So that means that the entries are actually correlated, right, often. Okay, and so the classical theory of extreme value statistics or the theory of records. So these are actually when the underlying variables are completely uncorrelated. And so the modern study of extreme value statistics is about when they are correlated, as is in many of these examples. So our main goal in this course would be to essentially study two models in parallel. So one is when they are uncorrelated. So we'll just, simplest classical model. So we'll recover all the theories of, I mean, even then it's quite non-trivial. I mean, but still you can solve everything exactly when the variables, when the entries are totally independent. So that we'll do. And at the same time, we want to see what is the role of correlations, how the correlations affect the statistics of extremes and records. And this will be the some other model. In particular, for example, I'll just do in detail the random walk model. And so the role of correlations, both for records and extremes. So that will be the the next, so basically we'll do two things in parallel, both uncorrelated models and the correlated models. And we want to see what can we say about the statistics of extremes and records. Okay? And so this is an example of a global warming studies using the record-breaking temperatures, for instance. So you see there's a lot of work which is being done. And as Sanjeev mentioned, I mean, this is the recent book that I wrote with my colleague Gregory Sher, and this is just published this year. So I'll just follow this book essentially, part of this book. I cannot follow everything, but okay, since I have 10 lectures, I can do some of the things in details. And there are many interesting things, as we'll see, because sometimes totally unexpected results, which are both mathematically interesting and also in terms of applications are very interesting. And so apart from this book, I mean, there are a few other references. So for instance, we wrote a review, kind of pedagogical review that I mean, you can look up. It's not very big. It's only 40-page review. Okay, and this is about the correlated random variables. Sanjeev has a lecture note which is on the archive. You can find. He gave a set of lectures on this in the RRI summer school. And there are a few other reviews that you can find. So these things will be useful for the course that I'll follow. And so this I'll not do it on the board, but I'll start with the simplest classical model, which is essentially the model where the entries are uncorrelated. So which means that the joint distribution, always have this picture at the back of your mind that you have n entries. It's a time series. It can be either eigenvalues of a random matrix or anything. And the simplest classical model is when they are independent and identically distributed. That means the joint distribution, it factorizes into individual distributions, P of xi, okay, each drawn from this. And so there is, for example, in the context of disordered systems, this could be the energy of different configuration, and the energies are totally uncorrelated, and this is what is called the famous random energy model of Derrida, and we'll see exactly work out these things in details. And for this case, all these extreme observables like, distribution of X max, X mean, or T max, T mean, order, gap, record statistics, everything can be computed exactly, as we'll see. And, but our main thing would be to go to understand also when this thing doesn't hold. That means when they are correlated, as I mentioned. So, okay, so this maybe at this point I'll just go to the board and work out these things, and then I'll also tell you why statistical thinking in terms of statistical physics actually helps to solve these problems. So So this is exactly 1 hour. Should we give a break or something, or come back? You can, Sanjeev, you can, now I'll go to the blackboard basically. So. Do you have some other? Great. Huh? Sorry? Huh? Yes. Yeah. No, the statement was that for the classical model is the when the entries are independent.
Oh.
Okay. So, and but most of the physics examples, of course, you will see that they are very strongly correlated, and so this is the sort of things that I'm going to discuss now. So. Yeah. So it's very simple actually to state the problem, so it's quite nice. इसमें लाइट है ना? Yeah. Start. Okay, so let's go back to our basic picture. You know, always keep this in mind that you have a time series of n entries, x1, x2, x3, xn. These are random variables. And we are interested, for example, just to start with the maximum of this set of random variables. And so these random variables are drawn from some underlying joint distribution. And the simplest classical model, as I said, and this is a very widely studied model both in statistics and physics, is this uncorrelated model or IID model. That means when there is no correlation between these variables x1, x2, x3, xn, which simply means that I can write down the joint distribution as if it factorizes. I can write down this as a product of individual distributions. Okay. So that means they are totally uncorrelated. Okay. In other words, if you calculate xi, xj, and this is this typical, standard definition of a correlation function. So this guy identically is 0. This is a connected correlation function. So if you just see, because there is no correlation between these particles, so the identical is 0. So this is the uncorrelated model, and for which you can actually, as I said, you can calculate everything exactly, and they're already quite interesting but non-trivial. Oops. And the second thing is that when there is presence of correlations, okay. And this simply means that you can no longer factorize this. It does not factorize into product of individual distributions. And then all this theory that you develop for this model does not work. And so the question is, what do we do when you have presence of correlations? There is no general theory for it. So what people try to do is to study different models, simple models where you can actually, solve or say something explicitly for this in the presence of correlations about these observables. And that's what, we will see some examples of that. But before I do that, so just to mention that why physics can be useful, the language of statistical physics. Okay? And that's actually easy to see. Why, you can cast the calculation of the, for example, statistics of X max in the language of the standard statistical physics. So let me just also, just to, I call it B joint, subscript joint, because, okay. So I want to calculate. So you have given me this P joint distribution, okay? So for the moment it will be general, not particular model specific, okay? Given P joint, if you can't see the letters I'm writing, please tell me. I'll try to dig at them. So our first problem is that given this, you want to compute the PDF of X max, okay? So PDF means probability density function of X max, which is this precisely the maximum. Okay. So it turns out, so I'll denote this PDF probability density by, let me use, P max of Xn. So this is the probability density that the X max random variable takes the value little x, okay, for a given n. So this is my task. So how do I compute this? Okay. So it turns out, and I will see in a minute why, that it's actually more convenient to study not the PDF of this P max, but its cumulative distribution. Which is defined as Q max of Wn. This is the probability that the X max is less than equal to W. So which is just the integral of, let's say, minus infinity to W of so this is just the cumulative distribution of the maximum. And if I know the cumulative distribution, then the PDF you can find out just by taking derivative of this equation, right? So P max of Wn is just so it turns out that this cumulative distribution is easier to compute than the PDF directly. And once you know the cumulative distribution, you can just take a derivative. Okay. So how do I compute this guy here? So what is this event? So this event is the probability that the X max, the maximum, is less than equal to W. Okay? So that means you have your entries, and you're asking what is the probability that all of them are less than some height W. Okay? But if X max, in this example, I mean, this guy is the X max. So you see, if X max is less than W, necessarily this is the same as the probability that all of them are less than equal to W. Right? Because if the maximum is less than W, that means necessarily that all of them are less than equal to W, okay, as you see from that picture. So how do I compute this? So if I know the joint distribution, then this is, by definition, is just this integral, right? Because when I'm asking with event that x1, x2, x3, all of them are less than equal to W. So if I know their joint distribution, then this is, sorry, this is just an n-fold integral where the limits are going from minus infinity to w. Okay? Very good. So now, let me write this as so I'll define, not define, just rewrite. Because my goal is to make some connection with statistical mechanics, and you will see that immediately. So rewrite using this following identity. You know, if you have a number z, you can always write down this as e to the power log z, right? Everybody knows this. So then I write down this p joint of x1, x2, x3, xn, which appears inside this multiple integral. I write down as exponential of log of p joint Why am I doing this? It will be clear in a minute. So then, what you have here is a multiple integral. Integral limits is from minus infinity to w, and then you have e to the power log p joint of x1, x2, xn. By the way, if you don't follow anything, please stop me, interrupt me, please feel free to ask questions. Okay, so I do like this. And now let me just call this log p. I'll define another object, e, which is a function of x1, x2, x3, xn. This is renaming as minus log p joint. Okay, just a renaming. So then this cumulative distribution q max of wn, which is this multiple integral there, but now things are looking familiar, right? Because what is this? This is exactly like a Boltzmann weight in a statistical mechanics system. I am assuming that all of you are familiar with basic statistical mechanics. So Boltzmann factor with the inverse temperature beta equal to 1. So this is like the Boltzmann factor, and therefore this is exactly like a partition function, okay? But it's a restricted partition function because the integrals are not going from minus infinity to plus infinity, it's going up to minus infinity to w. So what you have is just a reinterpretation. So we have a gas of particles and their positions are on a line. So one-dimensional gas. N particles and their positions are x1, x2, x3, xn. Okay? And they have an energy associated with this gas, which is, this minus log p, some function. And this is limits are from minus infinity to w, so that's like you have a hard wall at W. All the particles, they have to be less than or equal to W, right? So you have a gas of particles which is, freely varying from minus infinity to W. This is a hard wall. And they are interacting with each other through some energy, okay? And so this is your, this is exactly a stat mix system. And what you are interested is in calculate this object there is just the partition function of this gas with this restriction of hard wall, okay? And then you immediately see that this classical uncorrelated model, what does that mean? So in case, if it fact, this is a P joint. So if P joint factorizes, so then the energy of this configuration is just minus log of P joint, which is minus product becomes sum of log of P of xi. So this means that x1, x2, x3, x3, you see the energy is just a sum of terms. There is no cross terms. So that means it's an ideal gas in the physics language. Okay? And then this partition function, because the energy, just breaks out into, because this is just a sum of terms, there's no cross term, so you can actually, this whole thing, is just a product, it just becomes a product of the individual partition function, just using this. Right, because it's e to the power minus log of P of x, which is just a, e to the power minus, so it just becomes P of x dx. Okay, so this is, as you know, ideal gas, we can actually solve it because, the partition function just factorizes. They don't talk to each other, because there's no interaction between this set of particles. And we know how to solve ideal gas very well in statistical physics. We are taught always. So you see, when you cast in the language of physics, this classical model that a statistician study, the uncorrelated model, it actually becomes very simple. It's just an ideal gas. Okay. Of course, after that, you want to calculate several observables, and you have the added complication that there is a hard wall at W. You have to keep track of that. Okay. And we'll do that in detail. Okay. But there's an exact formula. Okay. This formula is exact. So in the classical model, if you tell me what is P of x, then you can calculate the distribution, and distribution for any n is given by the exact formula. And we'll later study, what happens in the large n limit. You will see that there are three, universality classes which comes out of this. It's very interesting. That we'll come back to that later. But let's continue with this. Okay. So now you see that immediately that whenever you have correlations between them, this is no longer true. That means, the E, the energy of the gas, it does not become sum of the individual energies. There are cross terms, right? Because the log P of x1 here in these things, the energy involves all the particles. It's not just, break up into individual particles. And therefore, what we have for this model is a correlated gas. And why, now immediately also see why physics can be useful, because I mean, we are taught in physics basically exactly this, that how to deal with an interacting gas, even when they are strongly interacting. And there are many methods, I mean, like, either exact results for some model examples, or renormalization group, or, various other techniques, path integral, and many other techniques that we know in physics. And we can actually employ those techniques to study this problem of extreme statistics, just because it is exactly mappable to an interacting gas or particles. But just only added complication is that you have a hard wall at W. Okay. So now let's look at some examples of correlations. So when you have correlations, there are two types of correlations. I'll distinguish between two types of correlations. So one is the weakly correlated gas. So this means that if I calculate exactly this correlation function Cij, that there is a typical correlation length, and it typically it decays exponentially as the distance between the, the I and j are the indices here. So I'm looking at, by distance I mean on the label space. So I'm looking at ith entry and jth entry. So it depends, let's say, on the difference between I and j with some finite correlation length. Okay? So that means, this guy is probably correlated only to a few guys here, and beyond that it's not correlated. And so this is the example of a correlation, weakly correlated gas, when psi, the correlation length, is finite. By finite, I mean that it's much, much less than the system size n. Okay? And the second example is a strongly correlated gas. And this means that the correlation length is much, much bigger than the system size. That means everybody is very correlated with everybody. Okay? So, and you will see many examples of that as I go along. Now, the weakly correlated gas is actually relatively easy to handle. How do I do that? I can erase this. And this is the idea of renormalization group in a very simple sense, in a kind of heuristic arguments. Okay. So again, think of this picture of the entries. So I have this. I should draw a bigger picture maybe, but okay. So let's try this. Okay. So I have a typical correlation length. What that means is that you can break the system. So step one, you break the system. By system, I mean the n entries into n over psi blocks, each with psi entries. So for example, if I have 100, and if my correlation length psi is 4, let's say 5, then I divide into 20 blocks, and in each block I have 5 entries. Okay, so in this example, suppose the correlation length is 2, let's say 2. So then I break this into blocks. So let me use a different color. So this is a block 1. This is block 2, block 3, block 4, etc. Okay. So now what we want to calculate is the X max, the maximum of all the entries, all n entries. Okay. So to do this, what we'll do first, that for each block, just locate the local maximum inside the box. Okay. So suppose, if this example, so in this first block here, this guy is the maximum. So let me call as Y1, which is the maximum of these 3 guys. And then in this block, this is the Y2, etc. Okay. So then you see that if I know this, so then the X max, which is the maximum of all guys, but this is also the maximum of Y1, Y2, Y n over psi, because I have n over psi such block maximum. So from each block, I locate the local maximum, and then my global maximum is just the maximum of all these guys. Okay. But the point is that these y's, which belong to different blocks, they are effectively, they are not really uncorrelated, but effectively uncorrelated, because finite correlation length means that beyond the correlation length, the guys are essentially uncorrelated. Okay, so this means that these guys there, these Y1, Y2, Y3, they are essentially uncorrelated. So if I know the distribution of Y1, Y2, etc., then I can use the theory of uncorrelated variables. On this block level, this is the idea of a real space renormalization group. So you see that this joint distribution, the distribution of the global maximum, then I can write down in terms of this distribution of the y guys, and it will be to the power n over psi, essentially. Okay. So approximately because it's a heuristic argument. Of course, there will be some guys which are close to the border between blocks, and they will be correlated, etc. So there will be, but roughly speaking, that this is again, this will be minus infinity to w of p of y to the power n over psi. Okay. So again, I have if I know how to compute the distribution of the little y's inside the block, then at least I know that what is the distribution. I can apply this theory. Of course, calculating this is not always easy, okay, because inside a block they are again strongly correlated, okay. So, but at least if you, for example, if you do simulations or something, you have a good idea of what this guy is, and then you can use this general formula for uncorrelated theory. So essentially, basically what it, in the RG sense, renormalization group language, what it means is that essentially it flows back to the fixed point of uncorrelated variables. Okay? So this is the case of weakly correlated variables. Now, strongly correlated means I cannot do this blocking, because the correlation length psi is much bigger than your system size n. Okay? So I cannot at all apply the theory of uncorrelated models. I have to find some other techniques. So this is like, again, in the language of phase transitions or critical phenomena or renormalization group language, this means that, it's a completely different fixed point. I cannot just do perturbatively around one fixed point and find out the solution. I mean, it's a completely different thing. I mean, they are strongly correlated. And so this means in the language of statistical mechanics, I have a gas which is not at all nothing to do with the ideal gas. It's completely strongly correlated gas. Everybody is correlated with everybody. And there, we don't have any theory for that. Okay? So for that, you need to solve, class of models to get more knowledge on and to develop, and that is where the field is right now at this stage. Okay, so let me give you one example of such strongly correlated system. And this is the first physics example I mentioned, example of strongly correlated system. Simplest example is 1D random walk sequence. So this means, again, think of this picture, but now xn, it is the location of the position of a random walker. So I'm thinking of random walk which takes place on a line. So your walker starts from the origin and it makes jumps like that. So the position of the walker at step n, it's a Markov process. I'll tell you what means Markov. Is the previous position plus some noise. So this noise, for example, it jumps from here to there. So therefore, this is the eta 1, if you like. And then this is eta 2. It jumps back, eta 3, etc. So this is the position of the walker. This is the noise. So these are increments, if you like. So eta n's, we assume that they are, just for simplicity, that they are independent from step to step. And let's assume also that they are drawn from an underlying distribution, each of them independently. A theta. Okay? And we'll also assume that this is symmetric, so that there is no overall bias. Okay? So several examples of A theta you can think of. So for example, the classic example is, this is what you are familiar with often. So this is called a lattice random walk. So eta, so this is delta function. That means eta is a random variable. It takes two values. Eta can be either +1, the increment, or -1 with probability half. With probability half. So that means basically the walk stays on integers, 0, 1, 2, 3, etc., -1. So you start from here, you jump either to this or to that with equal probability. And then if you come here, then again you jump back either here or you go to the next side with equal probability and so on. So you are always staying on the integer, on the Zn basically, okay? So this is an example of the lattice random walk, but this is actually much more general. It includes lattice random walk as a special case. You can have a theta, for instance, just a Gaussian. Sigma is the width of the distribution. So this is a Gaussian walk. So this is in continuous space. because the noise is continuous. You can have double exponential distribution like this. You can put a length scale if you like. This is sometimes called the Laplace distribution. Or you can have even the fourth example. For example, you can have this f of eta to be just uniform distribution between -1 to +1, the height, which is half. So that means you are choosing a random number uniformly between -1 and +1, okay, the flat distribution. So this is called the uniform random walk, and so on. And then yet another example that you can have f of eta. So in all these examples, what you see is that the jump is a finite amount, which means that if I calculate the eta square, the typical fluctuation width of the jump, so this is always finite, okay, in all these 4 examples. But you can have a case where f of eta has a fat tail, which decays very slowly on both sides. For instance, you can have f of eta going like 1 over eta to the power mu plus 1, where this exponent mu, let's say between 2 and 0. So this means that you actually jump, very long jumps. From here, you can have a very big jump, and big jump like that, okay, because there's a very high probability to have a very large eta. So these are called Levy flights. And this mu is called the Levy index. So if mu is between 0 and strictly less than 2 and positive, you see that, and you need mu plus 1 because in order that it's normalizable, basically. So it's normalizable, but its moment doesn't exist. So for example, if I look at the second moment, it's divergent. In all these examples, the second moment is finite, so that means the jumps are more or less of order 1, essentially. But here, the jumps can be very big, so second moment diverges, and these are called Levy flights. And when mu is exactly 2 or onwards, then the second, bigger than 2, then the second moment is finite. And whereas for mu between strictly less than 2 and bigger than 0, it's actually second moment diverges, okay? So second moment. So roughly speaking, these are random walks with very, very big jumps, essentially. Okay, so this is the definition of random walk. And now suppose that, if I plot a typical trajectory of this random walk, so again I plot xn versus n. It starts from the origin. We assume that, okay, so let's say we start from the origin. We're making jumps like this. Okay? So this is our, if you like, our values of xi's, the positions, they are the entries of the sequence. Now, why are they correlated? Because the noise, which is the implement, in the increment, the increments are uncorrelated, but the positions themselves are correlated. To see this, so suppose that I look at the xn, I just use this relation to, so for example, if I look at x2, x1, let's say x1 is eta 1, x2 is x1 plus eta 2, which means eta 1 plus eta 2. X3 is x2 plus eta 3, which is eta 3, and x2 is eta 1 plus eta 2. And so on. So in general, xn is just eta k. Okay. And now suppose that I calculate the correlation function, this connected correlation function we had defined before. Let's say xn, xn. Its mean value is 0, so therefore this is the connected correlation function. So what is the answer? So for example, I mean, let's look at just, let's take x1, which is eta 1, and x3, which is eta 1 plus eta 2 plus eta 3. Okay? So you see they are correlated, these two guys, because they share a common noise, eta 1. Okay? Even though etas are uncorrelated, if I calculate x1, x3, so this correlation is eta 1 square, which is non-zero. But this correlation is 0 because eta 1, eta 2 are uncorrelated. And this correlation is also 0. But this is non-zero, it's finite. Okay? So it's, let's say, sigma square, if the sigma square exists, like in all the examples. So in general, it's easy to see if you have xn, and so xn is this, and xm is k prime. So if I calculate xn, x prime, so the only thing is just like this example, you see it will be, common things will be the, first m or n, whichever is the minimum, right? So those will be the common things, and the rest will be all 0. So essentially this becomes sigma square times minimum of m and n, provided sigma square is finite. So you see, I mean, I take x1 and I take x47. They are very strongly connected. X1 and x47 will be again eta 1 square, because x1 will be this, and x47 will be eta 1 plus eta 2 plus eta 3 up to 47. When I calculate the correlation, it will be eta 1 square. So x1 is connected to x47, and everybody is connected to everybody. Okay? So this is a strongly correlated gas. There is no finite, it doesn't decay with the distance between m minus n, right? It stays fixed. Okay? So therefore, this is a strongly correlated. Simplest example of strongly correlated system. And in fact, if we cast in the language that we like, the particle problems, you immediately see what it looks like. So how do I write the joint distribution of x1, x2, xn? So I know that the f eta, the etas are uncorrelated, right? So I know the joint distribution of etas. So the joint distribution of etas the noise, so they are uncorrelated, so they're just a product of f of eta I. And this is the source of correlation. Now I have to translate that into the language of the correlation function. But since eta I is just, from this relation, you see this guy here, eta I is xi minus xi minus 1. So therefore this is, you can write this as product of So again, you see that it does not factorize into individual distribution of xi's. It involves the increment, the difference between two variables. Okay? So again, I can write down this as exponential sum over I log of f of xi minus 1. So I have a gas of particles with energy which is minus log of fxi minus. So for instance, an example, a familiar example is when you take f of eta to be Gaussian. Okay? Okay, with some normalization constant here. So now if I put this log of f, which is just a quadratic function here, so therefore the energy of your gas, which is minus I equal to 1 to n, because you want to write this as e to the power minus ei, E energy, log of f of xi minus 1. And so therefore, this is just f is e to the power minus x squared. So to take a log, just quadratic function will come there. So it's 1 over 2 sigma squared into xi . So it's like the statistical mechanics of the gas of particles is like a bunch of n guys which are connected by springs, if you like. So xi is the location. It's like a polymer. It's called the Rouse polymer chain. So each xi represents a monomer, if you like, and they are connected by a chain, spring constant, and spring constant is this constant 1 over sigma square, and this is just the energy, harmonic energy between these particles. Okay, and they can cross each other, of course, and this is the energy of your gas, and it's no longer factorizes. See, if it was factorizing into individual things, xi's, then that's like sitting in an external potential, but they are not talking to each other. They're totally non-interacting. But here you see the interaction is because of the harmonic interaction between two neighboring guys. And but this is a strongly correlated system, because as you just saw, that if you calculate the correlation function, everybody is correlated with everybody. Okay, so it says it's an example of strongly correlated gas, and this is precisely if you take the Gaussian distribution, then it's precisely the harmonic Rouse model of polymer chain. But if you take some other distribution, it will be some other gas basically. But it's always this kind of nearest neighbor gas which are interacting through each other. Nearest neighbor does not mean that it's a weakly correlated system, because as you saw in this example, they are nearest neighbor interaction, but the correlation is actually infinite. So there is no finite correlation length in this model. So this is sort of the example of the random walk. So I have 5 minutes, so let me just say, I'll just say what I'll do in the next lectures and what we are calculating. So this is one example. There are many examples. I gave you some other examples in the slides, but this is the simplest example, and we'll stick to this model. So the program would be that to calculate so computing the extreme statistics or other observables in this simple random walk model is highly non-trivial, as we'll see. Okay. So in the rest of the lectures, I'll just focus on two models, side by side, parallel if you like. So model 1 is this uncorrelated model, or ideal gas if you like in our language. And second example is this random walk example. So this is totally uncorrelated, and this is strongly correlated. Now both happens to be solvable exactly, at least for many of the observables. And so I want to show you how to calculate not just extreme statistics values, but, for example, time of the maximum or, other observables, record statistics, etc., how to calculate for these two observables. So what I'll do, so I'll calculate, just discuss several observables. So first observable, simplest, is what is called the survival probability, because this is related to extreme. So I'll discuss that because this sort of sets the stage, if you like. Or sometimes it's also called first passage probability. You'll see in a minute how it is related to extreme statistics. And then I'll discuss the extreme values. That means statistics of X max, this PDF, how to calculate this partition function of this gas, if you like, and what are the, sort of asymptotic large N properties which are universal, that does not depend on the underlying distributions. Okay, so universality. And then I'll talk about the distribution of T max and T mean, time at which the extreme occurs for both models. If time permits, I'll talk about the order statistics. That is the first minimum, second minimum, third minimum, etc., or maximum. And finally, the record statistics. So these are the observables, and for each observable, I'll discuss these two models just to illustrate that how correlations between these entries change the physics completely between the two cases. Okay, so this is the, so for each of these, I'll just work out in detail for these two models. Okay, so what I'll do in the next lecture is to start some basic tools, about the, because one of the classic, very basic tool for, at least for the random walk problem, and even for this model, is to, is to calculate the Green's function. That is, what is the probability that the walker goes from 0, to x in step n, and how that is related to, how that can be computed, and that's easy computation, because we'll need that calculation for later things. And then I'll come to this survival or first passage probability. What is first passage? Just one word, and then we'll finish. So, yeah. Oh, sorry. Sorry. Go ahead. Yeah. Yes. Show it. It's trivial, but show it. The Jacobian is 1 actually. You can go from change of variable from eta is to xi, and the Jacobian, because it involves diagonal matrices, so xi is xi minus 1 plus eta I, right? So the Jacobian is actually a diagonal matrix essentially. So that when you calculate the 1, it's 1 actually. So therefore you can compute.
So in this
Yeah.
example,
Yeah.
very confused about one thing. So if I take sigma, if I make sigma larger and larger, it looks like the spring constant goes to 0 in this energy expression.
Yes.
Which seems to me that the sigma going to infinity limit, there is no spring constant, and it apparently should become uncorrelated. But if I look at the correlation expression,
Yeah.
that blows up as I increase sigma.
No, see, I mean, okay, so again, it's a sigma square is, because you can scale it. See, sigma, you can scale the xi's, right, with sigma. So that's why, so you have to look at the scaled variable. So in this particular example, it's just a, just if you rescale the xi's by sigma, is the, it is always there. You cannot really take that limit xi goes to 0. You have to look at the scaled variable, basically. But on the other hand, sigma goes to 0 limit is interesting, because that means all of them are exactly equal, basically. So there's just one delta function point, basically. So, okay, so I wanted to just say one thing about this survival probability. Why is it related to extreme? So what is survival probability? So I have this system of these things. So you saw that this Q max, okay, so what is survival probability? Survival probability for a sequence of, so if I take a sequence of xn, let's say, so survival probability is just a probability that, all of them are less than equal to W. So it's the same as the cumulative distribution of extremes. So this is exactly in my notation, Q max of Wn. And interpretation is that what's the probability that all of them are less than equal to W. So if you think of it like a stochastic process, like a random walk, for instance, there is the probability that this process stays below the level W. Okay? And it's called survival because as if, the W is like an absorber. I mean, so if you touch that guy, you will die basically, okay? So survival means that the probability that you survive is probability that you don't touch that W, okay? So you stay below this level W up to step N, okay? So this is sometimes is in the physics literature, sometimes it's called persistence. Persistence means that you stay below, you persist in one phase, which is below W, okay? And if I know the survival probability, so survival probability is exactly the Q max of W and cumulative. So, and this is the object that physicists often study, and it's exactly related to the cumulative distribution of the extreme statistics. And the first passage probability, this you will see again, in many, many studies. First passage probability means that you want to know the first time you exceed the level W. Okay? So if you say TF is called the first passage time, okay? And so this is the first time we exceed W, okay? So this is usually, I don't know which notation I'm using, just one thing. I don't want to mix up notations. Okay. So this is the FWN. So this is the probability that the first time you exceed the level W at step N, let's say, okay? Probability that TF equal to N. So how do I calculate this probability of these things? So you see that this is very simple. This is just, if I know this object, this Q max, why is that? Because this is the survival probability up to step N minus 1, and this is the survival probability up to step N. So therefore, the difference is basically the flux of those configurations where the particle exceeds the level N, the level W between step N minus 1 and N, okay? So first passage is just, in the continuum language, this is just the minus del F del T, if you think of this as time. So it's just a negative time derivative of the survival probability, okay? So if I know this extreme value statistic Q max, it gives me access to survival probability as well as first passage probability. And we'll see that these objects are, even for a random walk like this guy, for a general random walk, these are highly non-trivial to compute. And there are some really beautiful properties which I'll discuss maybe in the next lecture. Okay, I think I'll stop there then. If you have any question, please ask. I mean, there's no. So basically, as I said, next lecture. I mean, this is essentially the program. I mean, there are some observables, and for each observable, I'll discuss the two models and see what it gives. Yeah.
If you have a strong correlation in the real space,
Yes.
it's usually like in the Fourier space you get right?
Not quite.
In the
Yeah, but the question is gets, you know, if you, for example, if I want to calculate the distribution of the X max, in the Fourier's language, it's very hard to, you know, FK doesn't have any simple interpretation like that, right? So in the Fourier, unfortunately, it doesn't help, basically. Okay. Yeah.
So the examples that you showed, the energies were just functions of position.
Yeah.
Do we also have examples where we have momenta, kinetic energy coming?
Yeah, that's, but then you have, I mean, this is because it was coming from time series, but then you have another degrees of freedom, basically. Momentum will be another degrees of freedom. You have to define your time series with some other objects, like which is the analog of momentum or something like that. I mean, so it's, here in the natural language, I mean, this is actually more related to cold atom systems. I mean, you can think of these, you know, the cold atoms with some sitting in a potential and interacting with each other. And somehow there the momentum is, I mean, their masses are very small, basically. So the momentum is not really, masses are very high, so momentum is, doesn't affect so much. Tomorrow at what time? 11, same time. Okay. Oh, sorry.